All right, good morning. I want to make a quick announcement about class today and class on Friday. The last 10 minutes of class today, I'll be going over the organization of your project. And class on Friday is going to be dedicated to your projects. So I'll be prepared to spend 5 minutes on each of the 11 projects, 4 to 5 minutes on each of the 11 projects. I'll come with some advice already prepared, but I want you to come with questions that you might have about your project. So we'll talk more about that at the end of class. I'll be sure that no matter where I am in covering the material, that by 10 of, and if I'm running over, someone raise their hand and say it's 10 of, so sometimes I lose track of the time. And the last 10 minutes we'll go over all the timelines and assignments and all of that stuff so that everybody's on board. Okay, so we will continue with regression today. And in particular, we want to look at the heights of the mothers and the fathers. We studied this at the beginning of the semester when we were looking at summary statistics. At that point, we were computing correlation coefficients between two numeric quantities, and that was mother's height and father's height, and we saw that they were positively correlated. This is a scatter plot where I've jittered the data a little bit because the heights are reported to the nearest inch, so it gives you a better sense of what the actual distribution would be. Okay. So we have father's height on the y-axis and mother's height on the x-axis. And we see that for the mothers who are taller than average, the fathers also tend to be taller than average. But there's a pretty, it's a weak correlation. It's not that bad, but it's not a really strong one like we saw with the crabs. So here are the summary statistics from those two variables, those two numeric variables, the mother's height and the father's height. On average, the mothers are 64 inches tall, and the spread, which says the SD, is how far away from the mean might you expect to see a mother's actual height. And 2.5 inches says you could easily see someone 2.5 or all the way up to 5 inches away from the average of 64 inches. The fathers, on the other hand, are 70.2 inches, and their spread's larger. It's 2.9 inches. So I have a question for you. What's missing from here in order for you to understand the relationship between mother's and father's heights? Do these four statistics capture that relationship? Yeah? Say that? The correlation coefficient? Right. There's no connection here between mother and father's height with looking at these summary statistics. Each pair of those summary statistics is based on the one variable, either mother's height or father's height, whereas a correlation coefficient says how do these vary together, and it measures linear association. The correlation is 0.34 between mother's height and father's height. So let's use this correlation coefficient. We can, as you know, we can fit a line to the data and ask ourselves a question. If we look at the group of mothers who are 66.5 inches tall, on average, what's the father's height? So that's looking at one of those vertical strips in the scatter plot, focusing in on all the moms who are 66.5 inches tall, and then looking at the average father's height. So we can actually fit the least squares line, and that's it right here. Father's height is, the intercept is 45.4 plus 0.39 is the slope times mother's height. And we plug in the mother's height and we get 71.1 inches. So that's a point that would be on a regression line, and it's that regression line's is the best fit for the graph of averages. But there's another way that we learned on Monday to also use the regression line, but a little bit more informally. And that's based on knowing that the slope is 0.39. That slope is actually the correlation coefficient times the SD of y over the SD of x. So the SD of father's height over the SD of mother's height. So another way to do this is saying, okay, for a mom who's 66.5 inches tall, how far above average is she? How many standard units above average is she? So that's the sort of division by the SD of x. So a mother who's 66.5 inches tall has a height that's 1 SD above average. The average is 64. The SD is 2.5. So when we do this conversion, we're converting into standard units and see that she's 1 standard unit above average. Those are standard units for the mother's heights. Everybody with me? So that regression line that we saw, how it's less steep than the SD line, and the less steep is the multiplication by the correlation coefficient. And so we say, well, then we expect the father to also be, on average, above average, but how far above average? Not also 1 SD above average, and this is where the correlation coefficient and the regression effect comes in. It's R times 1 SD above average, and R is 0.34. So we expect that the average father's height for a mother who is 1 SD above average is R times 1 SD above father's average. So here's that calculation. Is the father's average is 70.2, and then we add 0.34 is our correlation coefficient times the SD for the fathers, and we get 71.2. The reason why it's a little different from when I plugged it into the regression equation is just round off with to the first decimal place. So that's essentially using the regression line in a very informal way. It's using it knowing that what's going on with the regression line, or the least squares line, is that the slope is R SDY over SDX. So if we move up by 1 SD in terms of x, then the y should go up by R times SD of the y's. Okay. So here we go. This is essentially what we're doing is we have 64s right here. We go over by 1 SD in the mother's height, and that corresponds to, on our regression line, of going up by 0.34 SDs and the father's height. So essentially all we're doing is reading off a point from the regression line. For the mothers who are 66.5 inches tall, the fathers on average, not all of them, right? There's a lot of variation here, especially because our correlation coefficients is not really large. That on average they're about 71.2 inches tall. All right, so now we're going to turn the question around and say, okay, what's the average height of the women who are, well, it should be the mothers who are connected with the fathers. We don't know their actual marital status, but what's the average height of the mothers that are married to? I'll just use that because it's easier for me to then think of some other way to describe it. Fathers who are 71.2 inches tall. One over R times what?
Men are on the vertical axis and the women are on the horizontal axis.
Mm-hmm.
The relationship between women and men is going to be R, so we're flipping our axis. So the slope of our graph is going to be 1 over R.
So are you telling me that you're going to read it backwards?
I think
Or
that's what your question is asking.
is that what my question is asking? If I'm looking at the fathers, who are all 71.2 inches tall, roughly, what's the average height for the mothers? Does anyone think it should be shaking your head no. Warren, does your result give you 66 and a half?
It should. The 66.5 gave me 71.2.
So think about what the how this line was created. It was looking at the average of, for all the mothers who are 66 and a half, taking all those fathers and finding their average height. So it was actually taking the average of the, of course there aren't any fathers in that because of this issue with the reporting to the nearest inch, but you get the idea. Taking the average of all of them and then seeing what the height is. So I'm asking a slightly different question here. I'm saying taking all the fathers who are about 71 inches tall, what's the average height for the mothers? Is that the same group of people? So the first one says, take all the mothers who are about 66 and a half inches tall, what's the average father height? What I'm asking here is, take all the fathers who are about 71 inches tall, what's the average mother's height? Is that the same question? So what's the group that we are looking at? So we're looking at the group of couples, mothers and fathers, where we've restricted them to just those mothers and fathers where the father's 71 inches tall. So we can say, okay, of the fathers who are 71 inches tall, they are about an inch above average. In standard units, that's 1 divided by 2.9, or 0.34 standard units above average. So then we expect the mothers to be R times 0.34 above average. Or excuse me, yes, that's right, which is 0.12 above average. So I'm doing the same kind of calculation. I say, okay, how far above average is the father? He's 1 inch, which is 0.34 standard units. So we expect the mothers to also be above average, but not that far above. That's, again, this regression effect. We multiply by the correlation coefficient. And so we get 64.3. Not even close to 66.5. So what's going on? Yeah?
Why don't you simply use the regression line equation? Why do you have to do all these numbers?
So, good question. Because, in fact, there are 2 regression lines. There's the regression line for predicting father's height based on mother, and there's a regression line for predicting mother's height based on the father's. And so here's what I'm doing, which ideally I'd replot my data, and I'd put father's height on the x-axis, mother's height on the y-axis. But I want to make a point here is that what I did was I said, I'm looking at the fathers who are 71 inches tall. And I'm looking at all those fathers. That's that horizontal strip across. And I'm saying, on average, what's the mother's height? So that's looking at all those little dots that fall in between those 2 dashed lines. And I'm taking the average mother's height. And that's the green square. So what's going on here is you have to be careful in that the regression line only goes one way, right? When we were minimizing the sums of squares, it was yi, it was the father's height minus a prediction based on the mother's height. So if I'm going to go back to this picture, that line comes about by fitting roughly through the points of averages, the graph of averages. This graph of averages is the average father's height for every fixed mother's height. So that's based on predicting father's height when we're fixing and looking at a little narrow range of mother's height. On the other way around, I said, okay, let's look at the fathers who are specific height. That says I'm now fixing the fathers who are specific height, and I want to find the average mother's height. So those are different subsets of parents. There's some overlap, of course, but one is looking at the vertical strip, and the other is looking at the horizontal strip. I always think it's better not to use the same scatter plot, but to, in fact, sort of take this plot and rearrange it so that we're always sure that what we're doing is the variable that we're predicting, in this case, mother's height, should be on the vertical axis, and the father's height should be on the horizontal axis. So the lesson, if you will, is that you have to be careful. That regression line that you're using for predicting the regression line, the blue one I have here, you're using to predict father's height based on mother's height. And it's not the same line that you'd be using if you're predicting mother's height based on father's height. Instead, you'd be looking at that horizontal strip, and you get that green dot. And it makes more sense to flip your axes around and just do a refit. And so since you know how this works, what's the slope of the regression line for predicting mother's height based on father's height? What should that slope be? There's three things involved in the slope: the correlation coefficient, the SD of father's height, and the SD of mother's height. So this gets at what you were trying to do, I think. Do you want to volunteer?
I guess you just flip the SDs.
You just flip the SDs, that's right. So it's R times the SD of the mother's height divided by the SD of the father's height. That's exactly right. So there are two regression lines for any pair of variables. In this case, our pair is father's height and mother's height. So for any pair of variables, we could predict father's height based on mother's height, or we could predict mother's height based on father's height. Those are two different regression lines. They're not the same. So in one case, we looked at mothers that are 66.5 inches tall, and we said, what's the average father's height? And we found out they were 1 SD above average. The mothers were, and therefore the fathers on average would be R times 1 SD above average, which gave us 71.2. On the other way around, we're looking at fathers who are 71 inches tall. They were 1 inch, which was only about a third of an SD above average. And so the mothers we're then predicting was R times a third SD above average. So so is that clear? I now want to go on to a different topic. So there are two regression lines, and it's always best when you're looking at a regression line to have on the horizontal axis be the one that you are conditioning on or given, and on the y-axis the one that you are predicting or looking at the averages of. Because it can get pretty confusing if you flip it around. Okay. So the next thing is, so what might we do when we say, okay, yeah, the mothers who are 66.5 inches tall, on average the fathers are 71.2 inches tall. But we know that all the dads aren't 71.2 inches tall. There's an error associated with it. They're spread around that estimate, around that average. So how do we go about estimating the spread? Making a statement about the spread about the 71.2. So this is the spread of father's height. So what is a typical father? How far might a typical father deviate from 71.2 for all the mothers who are 66.5 inches tall? So we're still looking at this subgroup, and it's all couples where the mom is 66.5 inches tall. We know on average the dad is 71.2. And we're saying, but what's a typical deviation? That's where the root mean square error comes in. But now it's the root mean square error about that particular estimate. And that's the square root of 1 minus correlation squared times the SD of the father's height, which is 2.7. So we're not, because the correlation's not that strong, there's still a pretty large spread that we have about our average or our regression line, even when we're looking at a small group of mothers or a small group of parents. So that 0.34 is squared. We subtract it from 1, take the square root of it, and multiply that as a factor by the 2.9, and it gives us 2.7. On the other hand, if we look at it the other way around, for the fathers who are 71.2 inches tall, we said on average the mothers are 64.3 inches tall. And what is the error associated with that? What's the spread? How far away might we see a mother from that 64.3? Well, that's the square root of 1 minus r squared times the SD of the mother's height, which is about 2.4 inches. So overall, the spread for all the mothers is about 2.5, and this says that our the relationship is such that even when we know the father's height, there's still a lot of deviation from the average mother's height. So this is a picture of what's going on, is that if we look at a particular mother's height, 66.5 inches tall, right about here, and we come up to the regression line, which is red. We say, okay, that's my estimate for the father's height. The bars, the blue bars above and below, is saying, yeah, but it's really typical to get things this far away or so. This is plus or minus 2 standard errors for that regression line. So that's plus or minus 2 RMSEs, root mean square errors. And so when you look at this all along the whole regression line, you see that roughly 95% of the data are falling within plus or minus 2 RMSEs. And this is, again, based on the notion of, for a fixed mother's height, I'm going to estimate the father's height, and then I'm going to look at the spread, the typical spread of a father about that average. And that's why we say that the RMSE for a regression line is similar to the SD for an average. And here our regression line is this red line, and we go out plus or minus 2 RMSEs all along the regression line, and we get these sort of bars, or bands, I should say, these bands around the regression line. And that's similar to having an average and going out plus or minus 2 SDs from the average and saying, okay, what's the typical distance of an individual from the average? Other questions on that? No? All right, let's go through a little exercise here. So the greatest interest in the Kaiser birth weight data was to say, okay, what are some of the influential variables on the baby's birth weight? And so suppose we now have a woman who wasn't part of the study, and she comes in, and let's say the same era, because now most women don't smoke when they're pregnant. And there are lots of differences between the 1960s and the 2010. So a woman's 2 months pregnant, and I would ask you, what's your best prediction for the birth weight of her child? I don't give you any other information about her. What would you tell me? What's your best estimate for the birth weight of her child? How would you go about coming up with an estimate of that? You all looked at the birth weight a lot in the first couple of weeks of class, but that's a long time ago at this point.
Do we
Yeah?
use the other birth weights?
You have at your fingertips, you have, not here, but theoretically, hypothetically, you have all the data from the Kaiser study. You'd say the average of the birth weights from the Kaiser study. That's a pretty good thing to do, I would say. So if you know nothing about her, you would probably use the average birth weight from the Kaiser study, 119.6. And then what if she said, well, how far away might I be from 119.6? Or if you want to say, well, this is the average, but not everybody comes in at the average, how would you attach an error to that, and that would be the standard deviation for the birth weight. New question. Suppose you have available other information from the Kaiser study. You know the mother's, suppose you have other information from the Kaiser study, but you also have other information about the mother that you could measure. You can measure her height. You can measure her weight. You can measure the father of the child's height and the father of the child's weight. You can measure parity. Parity is this a firstborn child or not? Or how many, what order is it? So parity is 0 if it's her first child. It's 1 if it's her second child. It's 2 if it's her third. And believe it or not, in the Kaiser study, there's a parity of 13. And you might check on her smoking status. So if I asked you, what's the single best predictor for the baby's birth weight? That's sort of saying, if you could just pick one of those variables and measure it on this mother to try and get a better estimate of the baby's birth weight, which one would you pick? So what do you think? Which piece of information do you think would improve your prediction the most? Of all of that information there. What do you think? Nima? Mother's height? Why? She does, but she's got the genes from both mother and father, right? But why height as opposed to weight?
I guess I don't know the reason. I mean, it would probably be both.
Well, actually, there's probably is a good reason. You guys have looked at that relationship, remember? Yeah? That's a really good idea, and that is what we're going to do. But before we get there, I want to say, why do you think mother's weight wouldn't be quite as good a prediction as mother's height? Yeah?
Like I said, people are horizontally constrained.
People are not as horizontally constrained. Yes, we had that discussion last week. There's more of your environment can affect your weight than your height. And so your weight isn't quite as much purely determined by nature as your height is. What about parity? You don't think so? Like just knowing how many kids she's already had is not necessarily going to predict. How about smoking status? So let's go on. What's the typical... So one way to see if we're more accurate is also to look at the typical deviation, which we just talked about, and that was the SD of the birth weight. So I'm going to move on to what we were already speaking about, but could you do better if you know her height? And suppose you know she's 66.5 inches tall. Now what's your prediction? So how would you come up with a prediction? Same thing as what we did for heights of mothers and fathers. Now we have what's on the y-axis? Birth weight. What do you think about that correlation? It's pretty weak. It's like 0.2. So we have for the prediction 123. So for the moms who are 1 SD above average, we would expect their baby's birth weight to be not 1 SD above average, but R times 1 SD above average. And in this case, the correlation's 0.2. And so it would be 0.2 standard units above average. The standard deviation for birth weight's 18. And so we are then going to add 0.2 times 18 and get 123 as our estimate. So how good is that estimate? That comes in with our root mean square error. And it's 17.9. So in fact, because the correlation's so weak, we do have a smaller spread from 18.2 to 17.9, but it's not that much smaller. And I thought I would remind you first of where that formula, root 1 minus r squared times the SD of y, comes from. So if you take a look, we see it's a square root of yi minus the prediction, which is a plus bxi, based on the mother's height. And so this, if you sort of were able to do all the, plug in all the exact calculations for A and B and do a lot of grungy arithmetic, you get root 1 minus r squared times the SD of y.
Wait, did you forget to divide by either n or n minus?
You're right. I forgot to divide by 1 over n, or divide by n. Thank you. Yes, that should be divided by n. It's the average deviation, not the total deviation. That is another statistics that's useful, but not in this case. Okay, so do any of these do better? Mother's weight, father's height, father's weight, parity, previous births. Well, parity is previous births. And we're going to do exactly what you said. We're going to look at the correlations. And we see that the correlation between mother's birth weight and mother's weight is 0.15. Between birth weight and father's weight is 0.14. Between birth weight and father's height is 0.11. And so in this particular case, the correlation is quite weak, and I would have thought it would be around 0.2 as well, but it's not. So I don't know. I mean, that might just be an artifact of this particular set of data, most likely. And the correlation with parity is nearly 0. So that means that, yes, mother's height was the best predictor. But what about smoking status? How would you go about predicting birth weight based on smoking status? When you just have two, never smoked and now smoke. Let's simplify it. The mother's currently smoking, the mother never smoked. What would you do? So you no longer have two. Yes, is that a hand up? Yes? So that it's you have a really good idea there, and let me split it apart a little bit. You've noticed that there are the mothers who smoke and the mothers who don't smoke. So you'd like to do something different with each of those. But there's no other variable to do the regression line. I'm not allowing you another variable. There is, in fact, that's a really good thing to do. Is see if you split them and then still use mother's height, would you do better? But if you only had smoking status, what would you do? And you're on the right track. So if you only had smoking status, you would look at what? You going to say something? No? Yes? Right on. You would look at the average for the two groups, for each of the groups separately. That's the only thing you have is a way to split them into two different groups. So you could say, okay, my best predictor for the women who smoke is looking at the average birth weight for the women who smoke. And the best predictor for the women who don't smoke would be looking at the average for those who don't smoke. Just so you know, if you try to do a correlation in R on infants, on the birth weight with smoking status, if you've done your, and this is where it's really, where R is really handy in that if you have created the smoking status variable as a factor, a categorical variable, you'll get an error. And it says, hey, it's got to be numeric for me to calculate a correlation coefficient on it. So instead, we look at these two averages. The average birth weight for the smoker is 114. So the average baby's birth weight for the smoker is 114 ounces, and the average birth weight for the non-smokers is 122, or nearly 123. Yes?
Can we just subset the two
Yes,
groups?
you could, and do the averages. That's how you do it if you were, yes, right. But what error would you associate with that? What's that?
Wait. No, no, no.
So if we look at the SD among the smokers, the SD of birth weight, so what's a typical deviation of a birth weight for the smokers? It's about 18.1. And for the non-smokers, it's 17.1. But we want a single number that says how far away might it be? How do we combine these into one estimate? Well, we could look at a combination SD of sorts. We could say, well, for the smokers, I'm going to add up all my squared deviations. That's yi minus y bar smoker. For my non-smoker, I'm going to add up all my deviations. That's the actual birth weight from the average for the non-smokers. Square them, add them all up, and divide by the total number of babies and take the square root. And when we do that, that's essentially, I've jittered this so that we can see it. It's essentially saying, okay, I've got my plot of birth weights. I'm looking at the birth weight for all the mothers who never smoked and just the spread of the birth weight for the mothers who are currently smoking. There's my averages, and I can see what the two SDs are. And that's an alternative way to look at it. And you can do this really simply in R with the LM function. The LM function, your model now is birth weight is a function of smoking status. And because smoking status is a factor, a categorical variable, that function knows what to do with it. It does exactly what you guys said you should do with it. It fits the two averages. And it does that calculation from the previous page. And so it comes back saying, okay, it's 17.58 is the typical spread. So I don't know if you remember, but that's the smallest spread so far. And the other thing is you can come up with the estimate of those two averages. The way to look at it is that you are given something to an intercept, which is 122.7, and you're given something like, this is what you add on if the mother's currently smoking. So the intercept is for the moms who never smoked, and so that's your estimate, 122.8 for the moms who never smoked. And then you add on negative 8.7 if you're currently smoking, and you get 114.1. So it's very handy the way they do it is they build up little pieces. They start with the intercept, which is where everybody starts, and then you add on bits to get to the average for your group. So for the never smoker, there's nothing to add on. So you're 122.8. For the now smokers, you add on minus 8.7 to get 114.1. So within the LM function, you get all of that. It computes the sort of the averages for you, and it also says, okay, here's the standard error. Here's what you would expect the deviations to be. So what's interesting about that is that if you look at all the different characteristics that you could have taken and measured on that woman that walks in the door, thank you, that walks in the door, you're a little fast. You're anxious. If you take all the measurements on the woman that walks in the door, the single most important thing to determine the birth weight is whether she smokes or not. It's not how tall she is, how much she weighs, how tall the father is, how much he weighs, how many children she's had before or not. Smoking is reducing her baby's birth weight. So if she's not smoking, the average is 122.8. If she is smoking, it's only 114. You might say, why do we care? We care because smaller babies tend to have more health problems. And I'm going to stop here, and we'll have to do this conclusion later. And we'll switch over to the project update. All right. All right, so this week, what is this week going to look like? Thursday is your day for you to go to your team section. What should you be doing in that section this week? Completing your data description and beginning your informal analysis and doing your exploratory analysis, making some diagrams, some figures of your data. The other thing that you need to do is sign up for times for next week. And what do I mean by times for next week? Is on Monday, so I mentioned this in class, I think on this past Monday, or if not last Friday. Next week's Thanksgiving week, and so rather than hold the typical class on Monday and Wednesday, and rather than hold my office hours on Wednesday and Thanksgiving, instead I'm dedicating Monday to meeting with each group individually for 10 minutes. So I'm going to schedule a block of time. It'll be about 5 to 6 hours. I'm going to post it on BSpace. And what you're going to have to do is send me an email, and then I'll start filling in the schedule. So it's going to be first come, first served, and everybody should be at the meeting. So you guys have to talk amongst yourselves. Send me 3 time slots in case the others fill up. So you're going to meet with me on Monday for 10 minutes. Each person gets 1 minute of airtime about what they have done. And they should each bring something which they're going to leave with me. And that could be a single plot, a paragraph about a summary description of the data, or a data description. This is in lieu of your quiz. Okay? Yes?
So is it all of them or just one?
All of what?
So do we have to like have them write up the data?
Each person has one of those. Right. No duplication. The idea is that you're all doing something. Right.
So if we have 4 or 5 people in our group and we have a 10-minute
You,
slot,
it's roughly the same. That'll give me more time to spend with you so the next 5 minutes, we're going to discuss next steps. And so we'll have more time to discuss next steps. Yes?
Are the time slots throughout the
Yes, they're going to start at 8 in the morning and they're going to go till 5. Yes?
So for what was supposed to be, so one person needs to make a write-up and one person needs to be a plot, or are you saying that each person just has to bring?
Each person has to bring one thing. Excuse me, I got something caught in my throat. And that may be one of those things.
Okay, so what is the one per group mean then?
One, oh, I only want one data description from the group. I don't want everybody to bring pieces of the data description. Right. Okay. On Tuesday, you're to also go to your section for your team section. And you're going to also meet with the TAs. So I'm meeting the GSIs at Monday evening, and I'm going to convey to them where you guys are and what advice I've given you, so that the 3 of us, the 2 TAs and me, that we are all on the same page giving you the same advice. And you're going to meet with them. So you're going to work on your projects in section on Tuesday, and you're going to meet with them as well. So come to your team section, and you're all going to get 10 minutes on Tuesday. Okay. Beginning this week, I posted this on Monday. I don't know if any of you noticed. I posted a team log. So that's part of what you're turning in at the end. So it's just going to start this week of so essentially when you met and who was in attendance and what did you do. So you don't all have to meet all the time, but I want you guys to keep track of who's doing what. And this will be turned in with your report. So start keeping track with your team log. Okay, the remaining assignments for the course. So the quiz number 2 is the meeting on Monday. You've got your 1-minute description and the material that you're handed in, and any questions that so also, if you ask good questions, that's part of the back and forth. I want you to come having clearly thought about your project and having good questions about what next steps or things you found you don't know what to do. That's why I'm dedicating Friday for me to come in with some advice for you about your project and for you to also come with questions. And I can stay and do office hours again after class for that hour on Friday right here in the classroom. Homework number 7 I will post today. You'll have 2 weeks to do it. And that's going to be on regression and least squares and that sort of thing. Homework number 8 is project related. It's going to be your rough draft of your poster. So your final homework assignment is the rough draft of your poster, and it's due on the last day, technical official day of class on Friday, December 3rd. Later today, I'll post some templates for your poster on BSpace. So I said this a couple times already, but this Friday is the Q&A about your project. Each project will be discussed. Advice will be offered and come with questions. On Monday, I also posted what is expected in your final report, and I sent a broadcast email out to all of you. But just to go over it, there are essentially 5 sections to your report: introduction, background, data description, results, discussion. In that report guidelines, it says the kinds of things that I expect to see in that. The final report's 5 pages. That's it. 5 pages of text. It's not 1.5 spaced. It's not really long, okay? So you think about it, it's 5 pages, there are 5 sections. Your results is going to be the longest. So you're looking at, a short introduction that's a paragraph long, and a background that might be a paragraph long or a half a page or whatever, and a data description. So that sort of gives you an idea. Depending on your project, some of these might be longer or shorter than others of the. So each team member is responsible for one of the sections. So your name is going to be attached to one of those sections. But all team members are to have the opportunity to read the entire report through, offer up edits, and have the whole thing approved by all the team members. So the last page of the report is, you'll see this in the report guidelines, says, I have had the opportunity to read and comment on all sections of this report. So I want to pay particular attention to the results, because the person who's in charge of writing up the results is not the person who's doing all of the data analysis. So everyone should be doing some of the data analysis. There's informal, exploratory data analysis. There's formal, whether that is making hypothesis tests, confidence intervals, fitting a linear model, making a really nice map. And there are others that I can help with particular. In fact, that's what we can talk about on Friday, is some ideas for what your formal analysis might be. And plots are really important. So every team member must have some particular thing that they have done in the results part of the section. And if you're in charge of a figure, then you're writing the caption and providing that to the person in charge of the results section. If you're doing the summary statistics, you're writing up a rough draft of a paragraph that you're going to hand over to the person doing the results section. So the person in charge of the results is essentially fitting it all together, smoothing it out, and saying, and looking for the holes, and going back to people saying this isn't right or whatever, but you're not doing all of the analysis. Rubric. I have just moments ago published the rubric on the website, and I just want to bring it up to show it to you. Well, it's somewhere here. Well, I guess I could try to get it. So it's right here. And I might have lost my internet connection, so let's see. Yeah. Usually, did you see it? Oh. Go back to where? All right, somebody come up here and show me where it is.
Go right, and then go up.
Thank you. Good eyes. I've got too many windows open. By the way, these top 3 things across the top are poster templates, and I'll be posting those for you to help you come up with it. So here's the rubric, all the 5 parts. Notice there's a lot of emphasis on the plots, the informal analysis, and the formal analysis. Then in addition, There's the written presentation and the poster presentation, and I know they don't add to 50. The 50 is the total you can get, and the way it's working is that's the deduction, and that's because if you have a really poorly written report, doesn't matter how what you've done, it's impossible to read and understand, and you'll lose. So you won't go to negative. It'll go to 0 as the most. But clearly, what I want you to focus on is making sure that your written presentation and your poster presentation follow all of these things. Like they are clearly explaining the purpose, they're attractive in terms of design, they're correct in terms of punctuation, et cetera, and they accurately present your analysis. And the homework that you're handing in on the Friday is your draft poster. And what I will be doing is over that weekend, I'll be looking at all 24 posters and providing feedback to you so that you can have a really nice poster come the poster session on the following Wednesday. All right. So I'll see you all Friday at the latest.